All right, let's go over our gas laws test review. First off, we have some of the different laws we covered. Charles' law, V1 over T1 equals V2 over T2. This is a direct relationship between volume and temperature. When the pressure is constant, direct meaning as one goes up, the other goes up, or as one goes down, the other goes down. So, for instance, double V1, T1 would have to double as well. In Kelvin, of course, all the temperatures are in Kelvin for the gas laws. Then we have Boyle's law, P1 V1 equals P2 V2. This is an inverse relationship, meaning as one goes up, the other goes down. So if we double the pressure, the volume would have to be cut in half. And in this case, the temperature is what's constant. Guy-Lussac's law, direct, again, similar to Charles' law, but this one is pressure and temperature. Again, temperature has to be in Kelvin. The volume is constant this time. Then we have the ideal gas law, PV equals nRT, a relationship between the number of moles and pressure, volume, and temperature. And then we also have R, which is a constant, 0.0821 atmosphere liters per mole K if our pressure units are in atmospheres, 8.31 kPa liters per mole K if our pressure units are in kPa. If we put Charles, Boyle's, and Guy-Lussac's laws together, we get the combined gas law, P1 V1 over T1 equals P2 V2 over T2. And then also notice the asterisks to, again, emphasize what are direct and inverse relationships. So go ahead and make sure you got the right stuff for that. You will have a couple of questions on the test in which, given the relationship, you have to say, is this Boyle's law or Charles' law or whatever. So keep that in mind. All right, now we'll move on to pressure units, some of them anyway. And of course, they will be all on the test, just as they were on the quizzes. We did introduce a new one here, but really not going to spend much time on it because torr is pretty much the same thing as millimeters of mercury. 760 torr, 760 millimeters of mercury is 1 atmosphere. The one we're most likely to use, the kPa, 101.3 kPa, is also 1 atmosphere. Then we have a couple of conversions. 3.2 atmospheres into torr. 760 torr goes on top. The 1 atmosphere goes on the bottom so that the atmospheres get canceled out. We end up with 2432 torr. So that's basically a multiply. Next, for problem 4, we have 890 millimeters of mercury converted to atmospheres. Notice that the 1 atmosphere is on top now, whereas the 760 millimeters of mercury is on the bottom, the denominator of the fraction, so that it is the millimeters of mercury that's getting canceled out. So this one's basically a divide. And then converting from ATM to kPa in number 5, 2.7 ATM times 101.3 kPa divided by 1 atmosphere. Atmospheres cancel and we get 273.5 kPa. There won't be a lot of conversion problems per se, but you might have 1 or 2 that are just a direct comparison, and then also once or twice where you have to actually change the pressure units so that they fit that particular equation. Any questions on the conversions? Okay, 6. 1 mole of any gas has a volume of 22.4 liters. You might remember that from our mole unit. However, that is only true at STP, standard temperature and pressure. Okay, if it is not STP, it does not have to be 22.4. But though we ignored it in our stoichiometry unit all the time, it would say on the problems at STP. How do we get from Celsius to Kelvin? We add 273, and that'll give us our Kelvin amount. So 75 plus the 273 gives us 348 K. What is absolute zero? Two ways to think about it. One is the actual temperature. That is 0 K. So absolute zero is not in Celsius, not in Fahrenheit. It's in Kelvin, 0 Kelvin degrees. Or it's negative 273 degrees Celsius, and it's negative 400 something in Fahrenheit. So it's very, very cold. But we can also talk about what happens at that temperature, and basically we have no motion, no movement at all, even at the atomic level. If we could actually get things that cold, even the electrons would not have motion. Okay. The whole theory behind the way gases behave has to do with the kinetic energy theory of gases. Heat them up, kinetic energy increases, the molecules move faster, you have more collisions, pressure goes up, things like that. Opposite, cool them down, you have less kinetic energy, the molecules move slower, fewer collisions, less pressure. So in terms of kinetic energy, energy is the energy of motion. How fast, literally. There's an equation for kinetic energy which is dependent on velocity. So the more energy you have, think about it, when you warm up, it's easier to move around. The more energy you have, the faster you move. Well, for gases, the faster they move will then impact how much they collide. You could also think of it as, put a bunch of cars on a freeway. The faster they're going, the more likely you could have a collision than if they're going slower. So any questions on this first page? All right then. So here we have STP, standard temperature and pressure. Zero degrees or 273 K. Don't forget all temperatures have to be changed into Kelvin before we can put them in the equations. And the standard pressure is 1 atmosphere, but we may need it to be in kPa. Don't forget that 1 atmosphere equals 101.3 kPa. Are solids, liquids, or gases easier to compress? Gases, because there's a lot more empty space between the molecules. And that should make intuitive sense if you just think about solids for a moment. They're tightly packed. There's not a lot of room to compress. Think of a brick versus a sponge. Sponge has a lot of empty space inside to compress it. Value for R in the ideal gas law. Both of these will be on the test. The main thing to remember is the 0.0821 goes with the atmospheres. The 8.31 goes with the kPa pressure units. And in fact, if you took 0.0821 and multiplied it by 101.325, you would get the 8.31. So that's just as 1 atmosphere is 101.3 kPa, 0.0821 times 101.3 gets you to the 8.31. Why does pressure inside a container increase if more gas is added into the container? You could think of this two ways. The first way I have listed here, more gas means more collisions, more things bumping into each other and bumping into the sides of the container, and so the pressure increases. You could also think of it in terms of the ideal gas law. On one side you have PV, pressure and volume. On the other side of the equal sign, you have nRT, N being number of moles. Well, if the number of moles goes up and you don't change the volume, then the pressure has to go up as well so that you still have an equality. 14, if the volume of a container of a gas is doubled, what will happen to the pressure? Okay, remember that at constant temperature, the pressure and volume go in opposite directions. So if you double the volume, the pressure will be half of what it was. And there is a little algebra to demonstrate it. Note that what I did basically is say P2 had to be twice P1. The P's cancel out so that I'm left with V1 equals 2V2. But I want to know what V2 is. I want to know how the volume changed, and therefore you end up with half. That's the idea behind those things. 15. What happens to the temperature of a gas when it is compressed? Okay, remember that temperature and pressure are directly related. So as one goes up, the other goes up. As one goes down, the other goes down. So if it is compressed, you're pressing, you're squeezing, pressure is higher, temperature is higher, it increases. Now why? Basically, greater pressure means more collisions. The energy that is used to compress the gas is transformed into the speed the molecules are moving. They go faster, more collisions, and therefore the temperature increases. What is kinetic energy? Energy of motion. What happens to the pressure of a gas if the temperature of the gas decreases? Okay, again, pressure and temperature are directly related. So as one goes down, the other goes down. This one decreases. Lower temperature, fewer collisions. Fewer collisions means lower pressure. 18, what factors can cause an increase in the pressure of a gas? Lowering the volume, raising the temperature, or adding more gas molecules to the container can all increase the pressure of a gas. 19, what happens to the pressure of a gas if the temperature of the gas increases? Notice this is the opposite of question 17. And again, they're directly related. So as one goes up, the other goes up. So this one increases. Higher temperature, more collisions because they're moving around faster. So there's shorter time between collisions, higher pressure. 20, if the temperature remains constant and the volume is cut in half, what happens to the pressure? Again, they go in opposite directions. They're inversely related, so this one doubles. P1V1 equals P2V2. Notice that I just made the V2 be half of the V1, the V1s cancel, and I end up with P2 has to be twice P1. Whatever P1 is, P2 has to be twice it. 21 is actually just like question 20. It's just phrased a little differently. Instead of saying cut in half, we're going from 10 to 2. So I plug in the 10 for V1 and the 2 for V2, and then do the algebra, and I end up with P2 has to be 5 times the pressure of P1. But also recognize that the 2 liters is 1/5 of the 10 liters. So essentially, I cut the volume 5 times, which meant the pressure had to go up 5 times. 22, if a gas is heated, what happens to the volume of the gas if the pressure is constant? And again, direct relationship, V1 over T1, V2 over T2. As T goes up, V goes up. 23, yes, it's pressure and temperature, but again, written in that form, it's still a direct relationship. And so as one goes, the other goes. P changes the way T changes. Temperature increases, P increases. Temperature decreases, P decreases. And note, folks, how these two look, 22 and 23, versus the way 20 and 21 look. So when you have things side by side, PV, in 20 and 21, those are inversely related. When you have things on top of each other, the way you see in 22 and 23, those are directly related. And so, any questions on this page? Okay. Just a different wording of information I put at the beginning of the review. Pressure stays constant, volume and temperature are directly related. If temperature is constant, volume and pressure are directly related. So sometimes you're going to have a question on a test in which you'll get numbers, but sometimes all it'll say is things like, hey, if this one goes up, what happens to the other one? No numbers. Well, if they're directly related, it's got to go up too. If they're inversely related and the one goes up, then the other one goes down. Okay, a little bit of math examples here. 27, gas occupies a volume of 3 liters at 12.3 kPa pressure. What volume will the gas occupy at 80 kPa? Please note, all we've got in this problem is pressure and volume. So that's how we select the right equation, the one that just has pressure and volume. P1V1 equals P2V2. 12.3 kPa times 3 liters equals 80 kPa times V2. Divide both sides by the V2, and we end up with not quite half a liter. Now, let me point out, folks, that some of us have had a tendency to flip things accidentally. So if you were to write out 27 the way I've written it out, in other words, here's my P1, there's my V1, here's my P2, my V2, and then what you do is you go ahead and draw yourself a line, and then, hey, it's the 80 kPa that I need to get rid of so that on this side they get canceled. Then I have these ones straight. It's this times that divided by that. What I've noticed on some of the quizzes that we've had is people have a tendency to flip those because they don't actually write the equation down and then plug things in and then do the algebra. They think they can do the algebra in their head and then just write it down directly. And so sometimes we get it backwards. So one way to keep it straight is I wrote the equation, plug things in, and then actually put the algebra that I need to get the V2 by itself right there on the paper so that I keep it straight. And so here's my V2, 12.33, 80, and I end up with 0.46. Same thing with the next one, 28. This time we have a volume, temperature, new volume, new temperature, no pressure in this one, so it's just V1 over T1 equals V2 over T2. So I write out my equation, then I plug in the different things. Now, in a problem like this, again, just trying to help you keep things straight, we have the 20 milliliters over the 173 K. Okay, it had to be 173 because we got to be in Kelvin, equals the V2 over the 338 Kelvin. That came from the 65. Now, when I want to solve for this one, again, I have everything plugged in. I want to solve for it. Literally, I need to multiply on both sides. What's going on? There they cancel. And that gives me the right thing I need to find the V2 that's all by itself. So try not to do the algebra in your head. Go ahead and write it down on the piece of paper. It does make it easier. And so in this case, we get 39.1 milliliters for our V2. And then in 29, we have a volume, temperature, pressure, and then pressure, temperature. What's the new volume? I have two of everybody, two pressures, two volumes, two temperatures. So this is a combined gas law problem. P1 V1 over T1 equals P2 V2 over T2. It's the only time that I have everything. So again, plugging everything in equals what we have over here. In this case, if I want to get that V2 to be all by itself, all right, the way to do that is I then have to multiply both sides by the reciprocal, because in doing that, these will cancel and those will cancel, and all I'll have left is the V2. And of course, if I do it to one side, I have to do it to the other side. And so you can see here where I have the 293 over 40 times this. Another problem that I had noticed on the quizzes is you have to be careful when you're actually using your calculator. Calculation-wise, this is 100 times 2,000 times the 293, divide by 313, divide again by the 40. Two divides because I have two things in the denominator. Some of you have had a tendency to multiply these, then divide, and then because these are both on the bottom and you're thinking this times that, you then put in a multiply. But if you don't actually add some parentheses at the same time, you end up with a number that's way, way off, multiplying by 40 instead of dividing by 40. So this times this times this, divide, divide, and you get 4680.5 for the volume. So any questions on 27, 28, 29? One example each of those type of problems. Okay, 30. What does the ideal gas law allow us to find that the others do not? Number of moles or grams, because of course we can change moles into grams by taking the moles times the molar mass. Under what conditions does a real gas not behave like an ideal gas? Basically, things that are normal to us, relatively low pressures, relatively high temperatures, in other words, not big time negative. Real gases act like ideal gases. On the other hand, if we have really high pressure or really low temperatures, then real gases do not act like ideal gases. And this should actually make a little bit of intuitive sense again, because really, what's dry ice? Dry ice is solid CO2, which has been frozen. Well, how do we freeze it? We drop the temperature. So really low temperatures, way below zero, by the way, really low temperatures turn gases into liquids into solids. Obviously, if it's a solid, it's not going to behave like a gas anymore. Same thing with pressures, by the way. If you have a star or you have something like Jupiter, which is almost a star, The gravity is so great, the pressures are so great that hydrogen actually behaves as a solid on Jupiter, even though it's a gas here on Earth. Okay, diffusion. It's where a high concentration of a gas moves in a random fashion into areas of low concentration. No matter how concentrated the gas is in one part of the room, eventually it will fill the entire room evenly. Effusion is really very similar to diffusion. The difference is effusion is the process where the gas under pressure gets out of a hole. Think of like a hole in a tire or in a can. You might even hear the gas under pressure coming out through the hole to an area of lower pressure. We had that one question before, why does gas escape from a tire if it's got a hole in it? Pressure inside the tire is much higher than the pressure outside. Diffusion from high to low, always from high to low, even in our atmosphere from high to low. And as it moves from high to low, that's how we get winds created. Lighter gases effuse faster than heavier ones. I have mentioned before that you could think of the analogy of a car and a truck at a stop sign. Which one gets across the intersection first? Car does, because it's so much lighter, doesn't need as much energy to move about as the truck. We can actually make a direct comparison between different molecules if, for example, we were talking about, say, oxygen and hydrogen. Well, oxygen gas would have a mass of 32. Hydrogen gas would have a mass of 2. Hydrogen smaller, lighter. It will move around more quickly than the oxygen will. How many times more quickly? 16 times more quickly. If you just did the division, 32 over 2. So you can actually make a comparison between the different size molecules in terms of their mass for how much faster one should move than the other just by comparing their two masses. The only thing you have to remember is the smaller one will be going the faster amount. The bigger one would be, in this case, 16 times slower than the smaller one. Okay, then we have 34, 35. Couple of ideal gas problems. PV equals nRT. This one wants to know the number of grams, but to get to the number of grams, we have to know the number of moles. Now, as I said, here was a good place that people were messing up on the last quiz. If you had written down your equation and then said, okay, I want to get n by itself, that's what I want to solve for, then it would be clear that to get that, here the RTs cancel out, and I have n equals PV over RT. But I saw more than one person tell me that n was this because they never did this part. They just wrote that one down immediately. In other words, they did the algebra in their head and got it backwards. So if you literally write the equation down, that's why on the homework over and over again, I took off points. You didn't write your equation. When you write the equation down, and then let's say in this case, I want to find out t. Well, then to get t by itself, I end up with PV over NR. When we go over the quizzes, if you look at yours, you may find in some cases you flip them because you didn't do this part. You wrote that one down immediately. Okay, 1.2 atmospheres, we were given that. 2.5 liters, our volume, we were given that. 0.0821 for our R, because we're in atmospheres, and we had to change the 25 degrees into Kelvin. So 25 plus 273 gives us the 298. Solve for the moles, but this wants to know grams. So 0.123 moles times the 32 grams per mole gives us 3.9 grams. 35, what volume will 2 moles? So here we already have our N. That's N. 2 atmospheres, 40 degrees. Again, the 40 degrees has to be switched to Kelvin. The 2's will pretty much cancel out, leaving us just with these 2. And we end up with a volume of 25.7 liters. And then when you get to question 36, it's actually the same question 31 again. It got duplicated, so you don't have to answer it twice. Any questions on those?